Session 3, Network Data Delivery. Session 3, Network Data Delivery. Agenda of the session is data addressing and delivery, network connection mechanisms, and reliable delivery techniques. Data addressing and delivery include all these phases or steps: encapsulation, then fragmentation and reassembly, then connection control, then ordered delivery of packets, flow control, error control, addressing, multiplexing, transmission services. All these are part of activities, or you can say phases in the process from end to end data delivery from one node or one point to another. Let's go one by one to all these phases. Encapsulation. Data usually transferred in blocks. These blocks are known as protocol data units or PDUs. Each PDU contains data and control information. Three categories of control. One is address related control, error detecting code related control, and protocol control. Address consists of sender or receiver. Error detecting code, frame check sequences. That's example. Protocol control, additional information to implement protocol functions. That is a protocol data unit we are referring to, which contains data and control information. And when we say control information have these three categories: address control information, error detecting code, and protocol control. Then comes fragmentation and reassembly. Fragmentation exchange data between two entities, characterized as sequence of protocol data units of some bounded size, which means application level message. Lower level protocols may need to break data into smaller blocks. Communication network may only accept blocks of up to a certain size, means they are governed by size, they have limitation in terms of size. More efficient error control means smaller retransmissions that will allow. Fairer will prevent station monopolizing the medium, and then smaller buffer. Means fragmentation is important to have effective use of the channel, and reassembly of those fragmented packets or divided packets or divided blocks or divided protocol data units is necessity to make effective utilization, to avoid errors, and to prevent monopolizing the medium by one data or one node. That makes that becomes important and necessity, the fragmentation and reassembly. The segmented data must be reassembled into messages. From real life example, if you want to understand, that's quite easy. Think of an example of relocation service. I live in Delhi. I want to move my entire house to, I want to migrate, I want to shift to, let's say, Bangalore. Now, what will happen? How it will work? I have to put my entire household stuff into boxes, label them with proper heading, proper address where it will go. I will hire service providers, maybe truck owners or government like train or anything. Then I will label these packets or boxes that this has this material or this content, and then not necessarily all will be sent by one lorry or one truck, might be multiple vehicles used to transport those, and they may arrive at a different time with different routes. But dividing this is making effective use of the road transportation system. If I want to, I'm sending through the road transport and then reassembling them when I reach Bangalore is actually the same thing I'm talking about. Visualize that and you will get a better understanding of this. Segmenting, think of that if I put everything in one big container or might be a very big container, so it may not be possible or feasible to transport that in a single unit. Segmented data must be reassembled into messages, more complex if PDUs are out of order. Connection control, connectionless data transfer. Each PDU is treated independently. For example, datagram. Individual independent data blocks are sent, reorganized, reassembled when they reach, but each of them is independent of other. So that is independent. Second is connection oriented, like virtual circuit, like telephone line, like your one-to-one connection, conferencing cable or conferencing, yeah, Zoom meeting. This is connection oriented. Connection is established. If we are disconnected, you know what is happening. Like chat is connectionless or connection oriented. Chat is a very good example of connectionless. Connection is not necessary that you will always be connected. You send the message, you forget, and you get the reply once the system is connected. That's why you see different type of ticks in WhatsApp: single tick, double tick, blue tick, this tick, that tick, that signify what is status of my message. That is connectionless. Not necessarily the connection is always there. But video call, telephone call, the conference call, these are connection oriented data transfer. For example, virtual circuit, connection oriented preferred, even required for lengthy exchange of data or if protocol detail must be worked out dynamically. Phases of connection oriented transfer, step by step, the time is passing like this. Protocol entry, connection request, this is protocol entity and the packet. So connection request is made, connection is accepted, data is sent, multiple exchanges are happening, each data is being sent and acknowledged by the recipient, then connection termination request is sent and connection termination request accepted. So this is how the connection oriented transfer happens and the phases of connection oriented transfer. Data transfer and termination, both data and control information is exchanged. That means I'm talking about flow control and error control also. Data flow and acknowledgements may be in one or both directions. One side may send termination request or central authority might terminate the connection. Sequencing. Many connection oriented protocol use sequencing like packet sequencing so that we can reorganize the packets in the same order. HDLC, IEEE 802.11. These are all connection oriented protocols and they use sequencing. PDUs numbered sequentially. That means protocol data units which we use, they are numbered in sequence. Each side keep track of outgoing and incoming numbers. Then supports three main functions: ordered delivery, flow control, and error control. Then we have ordered delivery. Protocol data units may arrive out of order because of different paths through network. Imagine, visualize the example I quoted. Shifting house from Delhi to Bangalore. Three different containers or three different trucks carrying my household stuff. They may arrive in different time. So PDU's order must be maintained. Number protocol data units sequentially, easy to reorder received PDUs, finite sequence number field, numbers repeat modulo maximum number, maximum sequence number greater than maximum number of PDUs that could be outstanding. In fact, maximum number may need to be twice maximum number of PDUs that could be outstanding. For example, selective repeat. Flow control, how much data can transfer, can go at any point in time? How many are contenders? Who all are contenders to use the same channel? Like a traffic cop standing on a signal, allowing traffic from one road to move and holding others. That is for controlling the flow of traffic. So performed by receiving entity to limit amount or a rate of data sent. Stop and wait. Each PDU must acknowledged before next is sent. Credit, amount of data that can be sent without acknowledgement, that is credit. For example, HDLC sliding window. Then must be implemented in several protocols like network traffic control, buffer space, and application overflow. For example, waiting for disk accesses. Then we also need error control. This guard against loss or damage, error detection and retransmission. Sender inserts error detecting code in PDU. Function of other bits in the protocol data units. Receiver check code on incoming protocol data units. If error is found, then discard the unit. If transmitter does not get acknowledgement in reasonable time, then it needs to retransmit the same data again, same protocol data unit again. Error correction code enables receiver to detect and possibly correct errors. Error control is performed at various layers of protocol between station and network or inside network. Addressing consists of addressing level, scope, identifiers, and mode. TCP/IP concepts, transmission control protocol or internet protocol concepts. Host A, running application X and Y, need to communicate to X and Y application on host B. This happens on the TCP, transmission control protocol. The global network addresses are identified in IP, internet protocol. Then we have network access protocol. Then we have physical layers. So these are four layers in TCP/IP. Physical layer have the physical connectivity, that is physical using routers and physical cables and channels and fiber channel between different networks. So physical connectivity, so physical to physical happening at this level through routers, through channels, through cables, through bridges. So once the physical connection is established, we use network access protocol, that is subnetwork attachment pointless point addresses. Then we have IP and then the TCP. So this connection is logical connection. Physical connection had happen at the physical layer. This connection between application happens at the logical layer or logical connection. We call it as TCP connection or logical connection. Port or service access points are the points where the application is available. As an example, if I say mail, which works on port number 25, FTP, which works on port number 21 and 20, SSH, which works on port number 22. These ports are access points where the application is available. So that's a TCP/IP concept, basic concepts. Let's understand one by one. Connection identifier in our previous figure. Entity 1 on system A requests connection to entity 2 on system B using global address B2. B2 accept the connection. Connection identifier used by both entities for future transmission. reduced overhead, generally shorter than global identifiers. Then routing, fixed route may be defined. Connection identifier identifies route to intermediate systems. Then multiplexing, entity may wish more than one connection simultaneously, and protocol data unit must be identified by connection identifier. Use of state information, and then once connection is established, end systems can maintain state information about connection flow and error control using sequence numbers. Addressing mode, usually addressing refer to single system or port, as I was talking about, individual or unicast addresses. Address can refer to more than one entity or port, multiple simultaneous recipients for data, broadcast for all entities within domain, multicast for specific subset of entities. Network architecture features. When we are defining network architecture, what features we look for? Whatever we discussed so far should be part of our architecture design, like addressing, packet size, access mechanism, timeouts, error recovery, status reporting, routing, user access control, connection based or connectionless, what kind of networking it would be. Architectural approaches. There are two approaches as we discussed: connection oriented and connectionless. Connection oriented. We discussed that. It is a revision now, refreshing. Assume that each network is connection oriented. Is connect two or more network. It appears as ES to each network. Logical connection set up between each ES. Concatenation of logical connections over networks. Individual network virtual circuit joined by IS. May require enhancement of local network services like 802 or FDDI or datagram services. If you are using connectionless operation, then corresponds to datagram mechanism in packet switched network. Each NPDU treated separately. Network layer protocol common to all DTE and routers, known generally as Internet Protocol. Internet Protocol. One such Internet Protocol developed for ARPANET is RF791. Get it and study it if you want to study. That stands for request for comment. 791, that's all RFC stands for is the foundation for all network rules and regulations, and kind of what should I say, Constitution of India. The Constitution of India define that what articles that consist of articles which define what you can do, what you should do, what you should not do, what are your rights, legal rights, and what are your responsibilities. That's the same thing. The rules and articles are defined in RFC. Any RFC have one specific implementation or guidelines. Lower layer protocols need to access particular network. Connectionless networking, internetworking. Advantages: flexibility, robust, no unnecessary overhead. But it is unreliable because there's no guaranteed delivery, because you are not monitoring. Not guaranteed order of delivery. Packets can take different routes. Reliability is responsibility of next layer, that is TCP for example. IP operation, how internet protocol works. This example of IP, we have LAN 1 and LAN 2, the end systems. These are the layers of your TCP IP protocol, the router and the frame relay happening between the routers. So four layers are used: TCP layer, IP layer, logical layer, MAC address, and physical layer. So these are used, and see what is happening, how the headers are added. This H stands for header, HP header, and then TCP header. So the second layer, that is each layer have its own data and the extra headers attached, and then the reverse phase at this they are dropped. So headers are used by every layer to encapsulate the data and then passed on to the next layer. Design issues are routing, datagram lifetime, fragmentation and reassembly, error control, and flow. Routing. End systems and routers maintain routing tables. Indicate next order to which datagrams should be sent. Static routing and dynamic routing. There are two types of routing. Static may contain alternative routes. Dynamic is flexible, response to congestion and errors. Source routing. Source specify routes as sequential list of routes to be followed. That includes security and priority, everything. Then we have a route recording. That is how the packet from source will reach to destination. Dealing with failures. Reassembly may fail if some fragmentation or fragments get lost. Need to detect failures. Reassembly timeout assigned to first fragment to arrive. If timeout expires before all fragments arrive, discard partial data. Use packet lifetime, time to live in IP. If time to live run out, then kill the partial data. That is how to we deal with the failures, the communication timeout or connection failed. Similarly, we also need to understand the error control. No guaranteed delivery. Router should attempt to inform source if the packet is discarded. For example, time to live expiring. Source may modify transmission strategy if the failure is happening, may inform higher layer protocol, and datagram identification is needed. Look up the ISCMP, for example, which is your ping command. Flow control allows routers or stations to limit rate of incoming data. Limited in connectionless systems. Send flow control packets requesting reduced flow. For example, ICMP. IP services, that is Internet Protocol Services. Primitives, functions to be performed. Form of primitive implementation dependent. For example, subroutine call, send request transmission of data unit, deliver notify user of arrival of data unit, and parameters are used to pass data and control information in IP services. Options are security, source routing, route recording, stream identification, and timestamping. IPv4 header, Internet Protocol version 4. The header, what it consists of. There are 20 octets. The first one is version, then 4 to 8 is IHL, 8 to 16 type of service, and then total length. So this is identification part, first 8, then flag and fragmentation offset, fragment offset. Then we have time to live and protocol and header checksum, then source address, destination address, and options plus padding. This is what we have in IPv4 header. The data field carries user data from next layer up. Integer multiples of 8-bit long, that is octet. Max length of datagram, that is header plus data, is 65,535 octets. IPv4 address formats, network 7 bits and host 24 bits. We call it as class A address. In class B, network uses 14 bits and host use 16 bits, that's class B. In class C, 21 and 8 In class D, multicast, and class E, future use, which is not used. This is IPv4 address format. Subnet and subnet masks. Subnets allow arbitrary complexity of inter-networked LAN within organization, insulate overall internet from growth of network numbers and routing complexity. Site looks to rest of internet like single network. Each LAN assigns subnet number. Host portion of address partitioned into subnet number and host number. Local routers route within the subnetted mask or subnetted network. Subnet mask indicates which bits are subnet number and which are host number. Routing using subnets. The rest of the internet. So here we are talking about the LAN X, which is 192.228.17.32. Subnet number is 1. This IP address 192.228.17.33, 192.228.17.57, host number 25, and host number 1. This is basically LAN X. This is another LAN with another subnet number 2. So this is similarly we can LAN X, LAN Y, then LAN Z. Different LANs, different local area networks are connected using routers. This is router 1, this is router 2, and they are connected. That's all for this session. Thank you very much.